Sorry, usually would have done this at the beginning of the term, but I wasn't thinking I would record anything. Takes a little bit to get configured here. Okay. So, is my audio coming through okay? Emily, I see that you're signed in. You just,
Yeah, it's good.
yeah, that's, okay. Good. Oh, Emily, if you're trying to say something, you're muted. Sorry.
I wasn't. Your audio is fine.
And I still can't hear you for some reason. Well, try typing your message in the chat, maybe. So before we start, okay, good. So Emily said the audio is fine, but hers isn't for some reason. So before we start, just a couple reminders. I posted the first exam grades this morning just before class. I don't know if you had a chance to look, but please review my comments, and if you see any discrepancies, I'm happy to talk about them. And nobody's error-proof. If I overlook something, I'm happy to change your grade. Right. So also don't forget. The problem set I'm off screen there. I'll just forget this side of the board for our recordings. So problem set for due night. 11:59 p.m. And as I mentioned a couple times, extra office hours. Okay. 11:45 a.m. to 1:15 p.m. The same block. We would usually have them on Monday. Okay. Good. So yesterday, at the end of class, we just started talking about quotient rings, right? And basically all we did was say that without giving any precise definitions, we just said that Z mod MZ is an example of a quotient ring that we've been working with for most of the term, right? So let me just, I should say this. Looking at quotient rings, also known as, sometimes you'll see the word factor rings, or even drawing a more tight analogy with the number theory that we've done so far. Sometimes these are called residue class rings. And again, just when you look at other sources, I don't want you to be thrown for a loop as to these are all the same type of object. Okay. Right. So let's now start with some general definitions. Okay, so definition 1 are a ring. Here, we're not assuming anything. We're not assuming integral domain. We're just using ring like we have in our discussion so far. It's a commutative ring with a unit number 1. So R a ring. Then I, a subset of R, is called an ideal. If two things. Well, let me use Roman numerals here, actually. Roman numeral 1, if we take A and B in I, then A plus B is also in I. Secondly, we take A and I and R, little r, in the ring R, then AR, their product, is in I. Okay. That is, we may say I is closed under addition. And you may see this word in some sources. Absorb. So closed under addition is something that we talked about before, right? A ring is closed under addition. That's to say, if you take the sum of any two things, you remain in the set. Well, that's what we're saying about I here as well. Closed under addition. This term absorptive, this is to say, even when you take something not necessarily in I and multiply by something in I, you get absorbed into I. Right? That's kind of the motivation of that term. Okay. So we've seen many examples of an ideal already. Namely, I said this yesterday, right? I made a big deal about pointing out that MZ, the set of multiples of any integer M, satisfy these two properties, right? So think of MZ integers such that they are a multiple of M. Subset of Z. These are ideals in the integers. Okay, and in fact, we've also talked about ideals in a little bit more generality. Remember the proof we did yesterday of the fact that a Euclidean domain is a unique factorization domain. I asked you to think about, or we constructed this set that was all the finite linear combinations of some infinite set of elements of the ring, right? That successively divided one another. That's also an ideal. That's why I asked you to star this thing, because I want you to go back and look at what we did in that proof and make it reconcile with this definition. And I'll give you a second definition that will help you do that. Okay, so I, a subset of R, an ideal is said to be generated by collection of elements in R. Call them X1, X2, X3, so on. This is a possibly infinite collection of elements. if I consists of all finite linear combinations of the xi's. That is to say, I is equal to what we write. This is just a piece of notation first. Just in parentheses, we'll say x1, comma, x2, comma, all the way up to however many x's there are. This, a list separated by commas in parentheses means an ideal generated by this list. Okay, and we wrote down a practical description of this in the course of our proof from yesterday. R1 x1 plus R2 x2 plus all the way up to RK xk, where k is greater than or equal to 1, and Ri is an element of, or all elements of R. Right, this is just what we were looking at in the course of our proof yesterday, right? So basically, let me interlude this homework. Show that I form I equals the ideal generated by x1 through xk, say just the finite case, is an ideal by definition 1. Right, in other words, show that this is closed under addition and absorptive, right, which you can probably just do that right now if you want. Yes.
When the first definition, the closure under addition like follow directly from
Immediately.
properties of a ring.
Yeah. Yeah, that's what, exactly, right, so that's what I was saying, you could probably just think about this right now if you want. But, yeah. Good. Okay. So, let's continue, there's some more definitions we need here. Definition 3. An ideal I contained in a ring R is something called a principal ideal. If it is generated by a single element. Of R. That is to say, I is equal to the ideal generated by X, say, which again, I'll write explicitly, is just the multiples of X. Yeah, this is analogous to these ideals that we described MZ, right? Okay, and in fact, we sometimes denote this as little r, just like we wrote MZ here, right? In fact, a lot of what we'll do here is stated in slightly different language in chapter 4 of Professor Dummett's notes. And he uses this notation consistently. Little r. I find that this is more pervasive in your average source on number theory and ring theory. So I tend to stick with this, but we're gonna try to change between these freely. You know, it's best if you just are comfortable with everything, right? Okay. Okay, so here's a lemma. If now we assume R a Euclidean domain, then every ideal is principal. That is to say, every ideal has exactly, can be expressed as generated by a single element. Okay, so how do we know this? With no preparation, this is totally non-obvious. But I'll say this, we proved this lemma in the course of our proof yesterday. Okay. We proved this yesterday. How so? When we showed that an ideal I, i.e. something of this form, has an element y in I such that the Euclidean function evaluated on y is as small as possible. That is the smallest out of all the elements of I evaluated on the Euclidean function, right? Which we then showed means that y divides s or any s in I, right? So that is to say, this in turn implies that I is the ideal generated by y, this element that has smallest norm, or sorry, smallest Euclidean function. Yeah. So I'll leave this as an open box because I'm just reminding you of something we already did. And you could fill in a few more words here to make it fully precise argument on its own, but refer back to what I made you star yesterday. Okay. Okay. Good. So here's what I want to say now. One last definition for the moment. For a ring R with I and R and ideal. We form the quotient ring which we denote R mod I or R, well, actually, I'll just leave it at that at the moment, R mod I Which has as elements. So what I'm going to do here is just imitate exactly what the elements of the ring Z mod MZ are. I'm going to form residue classes. But now with regard to some general ideal I, not just MZ. Okay, so which has elements denoted. Sometimes we'll use the standard number theory notation, a bar, right? Or this is a more ring theoretical notation, a plus I. And both of these are notations for the set of elements B in the ring R, such that B minus A is an element of I. Okay. So let me just tell you what addition and multiplication are given by here. And then we'll go back for a second and interpret this in terms of Z mod MZ, our most familiar example. Okay. So addition in R mod I is given as A plus I plus B plus I. What do you think I should do here? What's the right definition to make?
So if we like just factor it all in together, like A plus B, since I is closed under addition, there will be some C that's also not.
Yeah, right. So remember, these are sets, right? So what we're doing here is defining a way to add together subsets of the ring R. And how we'll do that is just add together the representatives of each of these sets, A and B. And then look at the residue class, so to speak, of A plus B, right? So that is to say, we'll just do this. We'll look at the element A plus B in R, and then look at the set of, so let's write this out as a set. This is the set of elements C in R, such that C minus A plus B is in I. Yeah. You could analogously write this in a much more familiar fashion, right? If we just denote the residue classes by bar, just like we did for residue classes in Z mod MZ, how do we add these together? Well, we take the sum of the integers, A and B, and then look at the residue class of that. That's exactly what I've done here, just using this ring theoretical notation of plus I instead of bar. Yeah. Okay. And multiplication in R mod I, you may well guess, is exactly similar to what we do in Z mod MZ. We have A plus I times B plus I is just equal to AB plus I, or if you like, A bar B bar is equal to AB bar. You know? Really, it's not a whole lot going on here. Right? That's different from what we have been working with already. So, like I said, let's just go back and reinterpret some things in our most familiar setting. Right, so that is to say, example, in Z, an ideal must be of the form MZ for some M. Because of our lemma, right? We know that Z is the Euclidean domain, so every ideal has to be a principal ideal, meaning it's generated by exactly one element, or if I like, in my new notation, parentheses M. Right? So if we look at the mod I or the mod M, or if you like, in classic, the mod MZ. What do we have then? We have that for an example, I'll take some integer R. In fact, let me say I'll take two integers, R and S. Then I have two residue classes, right? R plus parenthesis M and S plus parenthesis M in Z mod parenthesis M. Okay, and if I want to add these together, well, what am I doing? I'm again just adding my two integers together in the integers and looking at the residue class mod n. Okay, so again, unfortunately, this is somewhat confusing, right? Because I have parentheses around the R plus S just to indicate that I'm adding them in the integers.
Just as like a pointer notation, it's like the Z parentheses and the most common form of expressing that.
So in the integers, because of historical reasons, this is the most common. But I just point this out because that's what makes it agree with other principal ideal domains. Right, because yeah, and I think that's why Professor Dunlap uses this consistently, just to make it more similar to the integers. But yeah, unfortunately, you'll see this for an arbitrary Euclidean domain most often. Yeah. Okay, so I just want to point out, really all I'm doing here, all we're doing here is reducing modulo M. Okay. So let me ask you a question. What if I take A and B integers and I look at the ideal consider the ideal generated by A and B. In the inverse. Okay. If I look back at my definitions, I know that I can generate some ideal with possibly an infinite number of generators. But by my lemma, I know that I can always find then a single generator afterward, regardless of how I originally thought of my ideal. That is to say, just because I took here 2 generators doesn't mean that I can't find a single generator that does the same job. So how do I find a single generator of this ideal generated by A and B? Sorry, what were you gonna say? Okay, let's unpack the definition first. Okay, what is the ideal generated by A and B? Well, this is the set of integral linear combinations XA plus YB such that X and Y are integers. Yeah. So can I find an element which divides all integral linear combinations? Yeah, it's the GCD of A and B, right? Good. And in fact, again, if you look back at the starred portion of yesterday's proof, that's exactly how we constructed that small element Y. Because we have the Euclidean algorithm and can construct a GCD, right? Then we have D equal to the GCD of A and B with the ideal generated by A and B equal to the ideal generated by D. Okay, so this is the case in any Euclidean domain an ideal with more than one generator is also generated by a GCD of the generators. Okay. Okay, let me pose you another question. Question. Can you describe the ideal generated by 1 in R any ring? What if I take 1 as a generator of an ideal in a ring R, any ring? Well, remember, this is the kind of the importance of that second property of ideals, that it absorbs any multiplication, right? So if 1 is a member of my ideal, then I can multiply any element of R by 1, and that must also be in my ideal. Which means that the ideal generated by 1 is the entire ring R. Okay? Any ideal which contains 1, the multiplicative identity in R, is the entire ring. So for example, the ideal generated by 1 is equal to the entire ring R. And you can check, of course, that R is an ideal of R because it's closed under addition and is absorptive. It already contains everything. So, okay, now. One last leading question related to the integers. Describe the ideal, which is generated by 3 and 5 in the integers. It's the ideal generated by 1, i.e. all of the integers, right? Yeah, good, because the GCD of 3 and 5 is 1, right? And based on what we were just saying, we have more than one generator. We can pare it down to a single generator by taking the GCD. And then with the second fact that we just deduced, we know that it's all of the integers, right? So it's generated by D of 3 and 5, which we know is 1, is all of the integers. Okay, good. So these are just some kind of like basic helpful facts that we using greater generality. There's okay. So let's talk about some of the other Euclidean domains and their ideals and what their quotient rings look like, right? We've kind of focused on two important classes of, well, I shouldn't say classes. We focused on two important examples of Euclidean domains outside Z, right? We talked about the Gaussian integers a lot, and we talked about polynomial rings with coefficients in a field. Okay, so let's see what we can say about these two rings. So if R is equal to F adjoint X for F some field, and Q of X some polynomial in R of degree D, then the polynomials of degree less than or equal to D minus 1 form representatives of all residue classes of F adjoint X mod the ideal generated by Q. Okay. So that is to say, remember, by residue class, I mean these sets that we have defined, right? So we're looking at some polynomial P of X plus the ideal generated by Q of X, right? For example. So we want to know what polynomials represent each of these classes, right? This is just like in the integers when, remember I told you that very often we like to work with the standard representatives. If you take Z mod MZ, each residue class can be represented by an integer less than M, right? So it becomes a little more complicated in say the polynomial ring or Z adjoint I, because things aren't ordered. We can't say less than Q of X, right? But you see again, this behavior of describing things in terms of a norm, right? We're looking at representatives are all less than the degree of the polynomial that generates the ideal we're modding by. Okay. So let's prove this. So by division with remainder, dividing any P of X in F adjoint X by Q of X gives the following. P of X is equal to Q of X times G of X for some polynomial G plus R of X, right? G being our quotient, R being our remainder. With the degree of R of X strictly less than the degree of Q of X, our divisor, which we assumed was D. Okay, so that is to say, sorry, I should have written this before, but another way of writing this is that P of X bar is equal to R of X bar, or I shouldn't put the bar here, sorry. R of X plus something in the ideal generated by Q, right? I have Q of X times some polynomial in F adjoint X, right? So this is just some element in this ideal. And so R of X is a representative for the residue class of P of X bar, right? Which has degree strictly less than D. Okay. So conversely, each residue class represented by a different polynomial of degree strictly less than d is distinct. Why is this? Well, we'll take R1 of x and R2 of x, both with a degree strictly less than d. If these are in the same residue class, if R1 of x and R2 of x in the same residue class, then we must have that their difference, R1 of x minus R2 of x, is in the ideal generated by Q. Right? Okay, so what does this mean? Well, remember, we assumed that Q was of degree D. And R1 and R2 both have degrees strictly less than D. So the only way this can happen is if K of x is equal to identically 0. Right? Okay. Right. So there you have it. Each of these polynomials of degree strictly less than d represents some residue class, and in fact, if they're different polynomials, they must represent different residue classes. That's the conclusion. Okay, so let's look at a concrete example. And this example is great because it points out, so far we've just kind of worked in abstraction, right? It's like, what are quotient rings really all about? What are they good for? This will illustrate this point. Okay, so let's take polynomials with real coefficients as our ring. And we'll take the ideal generated by the polynomial x squared plus 1. In R going x. And form the quotient ring R going x mod the ideal generated by x squared plus 1. Okay, so let's describe this ring in explicit detail. That is, let's talk about its multiplication and addition operations. Define how they work. Okay, so first, notice a complete set of representatives of our residue classes And given by what? What are the polynomials that represent all the residue classes in R join X mod parentheses X squared plus one? No. Okay. So the first thing to notice is that the generator of the ideal that we're modding by is degree two, right? So that means that all the polynomials of degree 0 and 1 will be the set of representatives of all the residue classes, or I should say a set of representatives of residue classes that will be useful to us. Okay, so it's given by the collection of polynomials of degree 0 and of degree 1. Okay. So that is to say, let me write this in symbolic form. R join X mod X squared plus 1 is equal to the set of polynomials of the form a plus b, sorry, a plus b x bar, such that a and b are real numbers. Okay, x bar here being the residue class of the polynomial x when we mod by this ideal, right? That is to say, if I'm talking about the elements of this ring are residue classes, then the variable in this polynomial has to be a residue class as well, right? Yeah. Oh, okay. Yeah, sorry. Okay. So addition is just like addition of polynomials. Addition is the same as addition of polynomials. What do I mean by this? Well, if I have two polynomials in the residue class ring, a plus b x bar, and I want to add that to another polynomial, c plus d x bar, I'll just add like terms. I'll add the constant terms and I'll add the linear terms together. Right, so this is to say I get a plus c plus b plus d x bar, and I get another polynomial of degree 0 or 1, depending on the values of a, c, b, and d. Yeah.
Those are parentheses.
These are we're not doing work with ideals here. We're just adding things together. Yeah. Well, also, if these were ideals, these are real numbers, right? So as long as they're not 0, this would be all real numbers.
Yeah. So we have x squared plus 1. When degree 0, 1 is constant.
So yeah, polynomials of degree 0 are just a constant polynomial.
Yeah, but so since 1 is contained, that wouldn't like it just be all of our adjoinings.
1 is not contained in this ideal, right? Because 1 is not a multiple of x squared plus 1. You can't come up with another polynomial to multiply x squared plus 1 by to get the constant polynomial of 1. So therefore, 1 is not a member of this ideal. Is that okay? Okay, so addition is just the same as it is for regular polynomials. Multiplication is the same as multiplication of polynomials subject to the constraint that x bar squared plus 1 is equal to 0. Right? Because remember, what we're doing when we modify an ideal is we send everything in that ideal to 0. So specifically, we're sending the generator to 0. When we look at the residue class of this polynomial in here, we know that's equal to 0. That's exactly what I've said here. Right? Okay, so let's see what happens when we multiply two polynomials of at most degree 1 together and see what we get. So we have a plus bx bar times c plus dx bar. Well, I'll just FOIL this like normal first, right? So what do I get? I get AC first outer plus a d x bar plus the inner bc x bar plus the last b d x bar squared. Okay, so now I will select like terms. AC, I'll put this here, plus BD x bar squared plus AD plus BC x bar. Now, here's where this relation comes in. X bar squared is equal to -1, right? So I'll just plug that in here. AC minus BD plus AD plus BC x bar. Does this look familiar? It's a type of multiplication that you're familiar with. Hint. Let me ask you a question. Or ask you to make a calculation. Quickly do that calculation for me. Multiply these two complex numbers together. What do you get? What was that?
Replace the, basically just replace R.
Yeah, you basically replace the X bar with an I, right?
If x bar squared is equal to -1, then x bar is not.
Yeah,
If you're for the relation that you use between the two lines.
the relation that X bar and I satisfy is the same. X bar squared is equal to -1, I squared is equal to -1. So we can interchange them. That's exactly what you were saying, right? Yeah, good. So just to reiterate, what do we get when we multiply these complex numbers together? A plus bi times c plus di is equal to, I'm gonna cheat here and just copy what I wrote over here. Plus, AD plus BC I. So that is to say, since x bar squared is equal to -1 and I squared is equal to -1, I and x bar are interchangeable. So what's the takeaway of all this? The ring R join X mod X squared plus 1 is the same as the complex numbers. Okay, so when you start studying arithmetic and then analysis, right? You successively build up structure, right? You build the integers from the natural numbers. You build the rational numbers from the integers. You build the real numbers from the rational numbers. How do you get to the complex numbers? Well, this is one algebraic way to build the complex numbers out of real polynomials, right? So this is a little more exotic. You have to take a step into the world of algebra to do this. Usually when you take complex analysis, if you have taken it or if you plan to, they'll just say at the beginning, so we're going to adjoin this formal thing I to the real numbers. This is actually what you're doing. You're forming the quotient ring of the polynomial ring R adjoin X mod, something that I satisfies. Okay. So let's take a break. It's pretty close to 11 already. Sorry. I know this might seem hopelessly abstract at the moment, but like I was saying yesterday, we're going to just finish this little abstract chunk today, and then we're going to go back to talking about some specific rings that will help us prove cubic reciprocity. I know this is a lot to take in at once, but after we go through a couple more examples today and then get back to some concrete rings that we want to work with, I think this will benefit us in the long run.
Were all of these things about rings formulated along the way to get to cubic reciprocity, or was the cubic reciprocity somehow formulated first, and then there was like a study of how actually?
Gauss conjectured mostly correctly, but couldn't provide any proofs. It took Yeah, so this whole theory of ideals is from like the 1840s, I want to say. I think the first full proof of cubic reciprocity was due to Eisenstein in the 1820s or 30s. So, you know, like in the decades leading up to when this was fully realized, people had some like idea of what was going on, but not really the language to talk about it. So I'd say half-half, right? So like people could definitely see the way towards what should be true for cubic reciprocity, but not necessarily able to prove it until the language got to a state where they could.
Looking at PDF of Discusiones Ars Graecas.
A translation, or were you looking at the Latin? Okay. Yeah, Latin's tough, from that era, especially.
I don't know how. Describing concepts like this. Also, rather impressed by their formatting. Everything is very like block justified and nice like hyphenated words.
Oh, yeah.
And the symbols like actually has like page breaks where it then like has big things of like piecewise functions. I'm just like not expecting that.
Yeah. That's when like printing was a lifetime work, right? So I'm sure that was a part of the impetus for that, right? It's like, this is all I do. This is what I do. I print things. So I'm gonna make it look really great.
Late 1700s lost hack.
Yeah, right. Way more impressive, right?
Okay, but you have like messes and everything's like really well formatted, so you're professionally doing it, and then you have like later on, we have people are making their own documents in house and things suddenly become like less formatted.
Yeah,
And then
yeah.
computers come, and things get more formatted again.
Right, there's kind of an ebb and flow there. You know, interesting, you were asking about the history of ideals. The reason ideals were introduced is because it turns out that, for example, for rings like z adjoint root -5, you can restore unique factorization if you talk about ideals instead of actual elements. And so that requires you to define a notion of what it means to multiply two ideals together. And then again, define what uniqueness means. But that was the motivation for developing ideals. And then all this business of generalized residue classes kind of came along with it. So pretty cool. Okay, I think everybody's back now, so maybe let's continue. So the important thing about this example is that we started with the ring of real polynomials, right? Which is an integral domain, but not a field, right? Most all elements, all but the non-zero constant polynomials are not invertible in R join X, right? And then by taking a certain quotient, forming a certain quotient ring, I got to a field. So this is interesting, right? Note here, by taking a quotient, I produced a field. We would like to describe when this happens in general. And in fact, it has a really nice answer. So first, a quick definition. R a ring, any old ring. I and R an ideal with I not equal to the whole ring R. Then I is a maximum ideal. If for any other ideal, J, so that I is contained in J is contained in R. We must have either I is equal to J or J is equal to all of R. What is the point of this definition? We're saying that there is no ideal that properly contains I other than the entire ring R. Okay. That is, there is no ideal properly containing I except the whole ring R. Okay, now any guesses what the maximal ideals are in the integers? For which M is MZ a maximal ideal of Z?
All non-zero issues.
Not quite, not quite. Let's write this down. Which integers M have MZ maximal in Z? Yeah, when M is prime, exactly. Why is that?
First we can express express it as.
Even if you don't have a complete justification, your intuition is great. Okay, exactly when M is prime. Okay, in fact, this is true in general. Let's prove it. Yeah,
But, the primes are not first on the addition, so how is there, an ideal in I? That is made of solely prime.
it's not made, I'm saying when M is any prime, you form the ideal MZ,
That's the
multiples of any prime. Yeah, if you just take all the multiples of a prime, there's no ideal that contains all of those. That isn't the entire ring. So this is true in any Euclidean domain. Let's prove it in general, and then we'll come back and interpret it here. Okay? So now we're going to assume R is a Euclidean domain. What do I want to say? And we'll take P an element of R. Then the ideal generated by P, PR, is maximal if and only if P a prime element okay. So here's a quick proof. Suppose there exists little r in R with the following containments. The ideal generated by P is contained in the ideal generated by R is contained in R. Right? I can do this with impunity, choose a single element, because I'm in a Euclidean domain. I know that all my ideals are principal. Every ideal has exactly one generator. I can write it in that form. I should say. Okay, so I suppose there is such a R. Well, this is the case if and only if P is equal to R times K. For some K in R, right? P itself is contained in the ideal generated by P, right? And if this whole ideal is contained in the ideal generated by R, that means P itself must be in the ideal generated by R as well, meaning that it is some multiple of R. You know? Okay. So then either R is an associate of P, K a unit, in which case the ideal generated by P is equal to the ideal generated by R. right? Why is this? If R is an associative P and K is a unit, how do I know that the ideal generated by P is equal to the ideal generated by R?
So P is the whole scope of R, so anything can created by the generation P is created by the generation of R.
Yeah, if K is a unit, I can just multiply by the inverse of K and express R as a multiple of P, meaning that the generator of the ideal generated by R is contained in the ideal generated by P. So it has to have everything that is in the ideal generated by R. So they have to be equal. They're contained in each other. Okay, good. Or alternatively, neither K nor R is a unit. Which implies that P is reducible, right? We've written a factorization of P where neither factor is a unit, if that's the case, right? Is reducible. Now remember the key result that, yeah,
We're in Euclidean domain.
we're in a Euclidean domain, so irreducible and prime mean the same thing, right? Okay. So how do I reinterpret this for Z? Just put a Z everywhere I have R here. Capital R. Okay. Good. So. Now we can answer this question. When is it that we take a quotient, we get a field? R mod I is a field. If and only if I is maximal. A pretty nice result, right?
I is maximal to R.
Yeah, good. Is a maximal ideal in R. Yeah, so I mean, ideal in R is kind of implicit because I wouldn't be able to pick it up otherwise, but yeah, that's what we're saying. Okay, so before we prove this, just one note. Note. This applies for any ring R, but when R Euclidean, we know that I, a maximal ideal, is just generated by a single prime element. So we're only going to prove it in the Euclidean case, because that's all we're going to need for the rest of the term. But you should know that this applies in general. Okay. Proof. Euclidean R. Okay, so let's start with the backwards direction. We'll assume I is maximal. That is to say, P a prime element. Okay. Then we have a couple cases. Right? If P divides A. For some A in R. Then the residue class of A is the residue class of 0 in R mod I. Right? Okay. So what happens if P does not divide A? Well, then what we have is that then a GCD of P and A is 1, right? That's relative primitivity, same as for the integers, except we say it's just A GCD. So that means by Bethu's theorem, i.e. the Euclidean algorithm, we can find R and S such that RP plus SA is equal to 1 in R. And so moving to R mod I, that is, I want to take this equation and look at it in R mod I. What do I get? I get, what's the residue class of RP? It's 0, right? I have a multiple of P in here. So I get 0 bar plus SA bar equals 1 bar. Or rearranging this. Or actually not, forget rearranging. This just the plot implies that I have S bar times A bar is equal to 1 bar. And so A bar is a unit of R mod I. Right? These are the two cases, right? Either P divides A or P does not divide A. If P divides A, I get sent to the 0 residue class. And if it does not divide A, I get sent to some residue class, which is invertible. So R mod I is a field. All the non-zero residue classes are invertible. Okay, let's now look at the forward direction. We'll assume R mod I a field. If A and B are elements of R, and we'll assume that P divides A times B, then what we know is that the residue class of AB bar, is equal to 0 bar in R mod I. Now, since R mod I is a field, we know in particular that it's an integral domain, right? It has no 0 divisors. So what that tells us is that one of the residue classes, A bar or B bar, must be 0, right? So since R mod I a field, it is integral domain. Which implies A bar is equal to 0 bar, or B bar is equal to 0 bar in R mod I. In other words, B divides A or B divides B. Right? B is a prime element. Okay. Good. So, let's see in practice what happens in the Gaussian integers when we quotient by a maximal ideal. So I want you to recall in Z adjoint I, sorry, let me just write this without. 2 plus I is irreducible and hence prime. Right, prime because Z adjoint I is a Euclidean domain. Remind me again why the element 2 plus I is irreducible in Z adjoint I. Remember, we saw this when we exhibited 2 plus I as a factor of 5 in Z adjoint I. And how did we show that it was irreducible?
It's, not a, it's obviously not,
It's not a unit, good.
if you were to try to factor 2 plus I into 2 elements of Gaussian integers, you wouldn't be able to express it with like the units of the Gaussian integers because you know like solid form.
Okay, so it really depends on the norm of this number, this Gaussian integer. Right, so let's just remind ourselves, since the norm of 2 plus I equals 5, right? And if 2 plus I was equal to alpha times beta, where alpha and beta are 2 Gaussian integers, then the norm of alpha beta is equal to the norm of alpha, the norm of beta equals 5. The only factors of 5 are 5 and 1, or -5 and -1, right? So that implies that one of these would have to be a unit if we came up with some factorization for 2 plus I. So therefore it's irreducible because the norm is a prime integer, right? Okay, so here's what I want to do. I want to determine the structure of Z adjoint I mod the ideal generated by 2 plus I. Okay, so, again, what am I really doing here? I'm trying to characterize the possible remainders I could get when dividing any element of Z adjoint I by the generator, 2 plus I. Right? Yes.
There's some theory that 2 plus I is prime, then this can be a field.
Okay, good. This will be a field. Which one? There's lots of fields, right? There's a field for every prime. There's also the rational numbers, the real numbers, the complex numbers. And there's a lot more than that too that we haven't discussed. But I'll give you a hint, this is one that we have discussed.
Not something silly like F join I.
No. I see where you're coming at there, but so let's just puzzle out here what we can say about the possible remainders of any Gaussian integer when we divide by 2 plus I. What do we know by virtue of Z adjoint I being a Euclidean function? Yeah, sorry. Z adjoint I being a Euclidean domain, possessing a Euclidean function.
Is it a norm max of all the elements I was in?
Yeah, okay, good. That is absolutely correct. And there's something that we can say that's slightly more helpful than that, but that's a good place to start. Okay. So let's write that down. For any X in Z adjoint I. Oh, sorry, that's not what I meant to say. What I meant to say was, for X, any remainder when dividing by 2 plus I in Z adjoint I, we have, this is what Wallace said, the norm of X, the remainder, has to be strictly less than the norm of the thing we're dividing by, 2 plus I, which is equal to 5. Better yet, you go back in the proof, look at the proof that Z adjoint I is a Euclidean domain. Remember, we showed that the norm of X, so in fact, the norm of X is less than or equal to 1/2 the norm of the divisor. Remember this? This is how we actually got our hands on this, by showing that the norm of the remainder was even less than a specific thing, less than the norm of the divisor. Or 5/2. Okay, so the norm of any remainder when dividing by 2 plus I has to be less than or equal to 5/2. The norm is always an integer, right? So what does that tell us for the possible norms of X? I'll say this and then we'll stop. Since the norm has to be an integer, what can we say about the norm of X if we know it's bound above by 5/2? Yeah, it's 0, 1, or 2, right? Good. So this gives us a good handle on what we're looking for. We just have to describe all the elements of Z adjoin I with norm 0, 1, or 2. Well, there's only one element with norm 0, that's 0. The elements of norm 1 are exactly the units, right? What are the elements of norm 2?
Plus or minus 1, plus or minus that.
Yeah, good. It's the 4, that is to say, the norm of plus or minus 1, plus or minus I. Any combination of pluses and minuses here, give you 2. Okay, so we've come up with a list of 1 plus 4 plus 4, 9 total elements of norm 0, 1, or 2. Tomorrow, we'll determine what field this is using this information. Okay? Have a good afternoon, and maybe see some of you in a short while. Oh, thanks. Yeah. Yeah. Good annotations.